All right, well, hey everybody. So I'm here to talk about Lecture 13, which introduces the idea of power, and just for fun, we're going to relate it to drag racing. Hopefully you enjoyed my last lecture, which my cat Polo sat prominently on my display the entire time. We'll see. He's crawling around. He's in a good mood, so he might come up, hang out with us in a minute. But last time we talked about kinetic energy and potential energy. I think it was the first time that we introduced that concept. And in the absence of friction, those things are constant. If you have friction, it's still constant. It's just that your total energy is a constant, but you're losing energy to friction that you can't get back because friction is related to thermal stuff and things getting hot. We did a worksheet on this scenario, in which you sort of launch this object from different angles, and you find that, in fact, the speed when it hits the ground is the same. Now, the time in the air is not the same. The specific x and y component velocities are not the same, but the speed, which is vx squared plus vy squared, the square root of that, the speed is the same. And when I say the final speed, what I'm talking about is the speed, just the moment before that it hits the ground. Obviously, after it hits the ground, eventually the speed is 0. But anyway, we did a worksheet on that, and you used midterm 1 type methods to show that the speed is the same, and then you used energy conservation, and hopefully you found that it was much easier to use energy conservation to show that this is true than it is to use midterm 1 type things, which involves quadratic equation, all sorts of unpleasant things. So I'm going to introduce the idea of power today. And so power is how many joules of energy are used over some interval of time. So this is joules. Typically this is seconds, so joules per second is a typical unit for power. We're going to call that unit watt, which is named after James Watt from England, who made steam engines and all that stuff. So this is what we'll refer to it as. Here's an example problem. I'm not really supposed to talk about electric stuff in this course, but just to give you an example, for a long time I drove an electric car that the fastest you could charge it at was 3.3 kilowatts. And the battery that it had was 17 kilowatt hours. So how long does it take to charge that battery? So the energy is 17 kilowatt hours, which we could convert to joules if we wanted to, right? So kilo is 1,000, so 17,000 watts, that's energy per second, joules per second, times an hour. So we could figure out how many joules this is if we wanted to, but in these units it's a little bit more convenient just to keep them in the units that they are, and so, okay, 17 kilowatt hours divided by the power, 3.3 kilowatts, that means that it takes 5.2 hours to charge up the car. And sure enough, if that car that I used to drive is all the way depleted of charge, it takes 5 hours or so to get it all charged up on a 3.3 kilowatt charger. So that's a nice example of this. Thankfully my car now can, I can charge it with much higher power, so I have a Nissan Leaf now. Anyway, how many joules is 17 kilowatt hours? So you can multiply it out like this. It's quite a lot of joules, by the way. But it takes a lot of joules to drive a car, so there you go. Alright, so today we're going to talk about, I think this is really fun. So the car I used to drive, and the car that's described here, is this electric smart car thing. So I'm going to switch to the video that has the electric car drag racing different cars. Now this video would only work outside of the United States because the electric car is going to lose every time. But they argue that the first few seconds the electric car accelerates rather quickly, which is what we're going to talk about. We're going to sort of break down this video as it goes. So let me mute my microphone, see if I can get this to work.
smart.
All right, so there you go. So clearly that car commercial would never work in America. It's only in Canada would work. But I used to drive this car. It was a really fun car to drive. Accelerates really fast. The top speed is not so much, but it can really accelerate. It was pretty fun to drive as a result. So let's break this down. And how is it possible that this electric car can be faster for the first 5 meters, but then be much slower for the rest? So we're going to sort of break this down. And here's what we know about the smart car. So this is what I like to do. I like to just look up the numbers, and I don't know anything about the speed of the car, and just try to figure out some basic parameters on how it might speed up. So the electric motor in this car is rated at 30 kilowatts, and the mass of it is about 1,000 kilograms. And so if we assume that all of the power, all this 30 kilowatts of power in the motor gets converted into the kinetic energy of the car. So for example, if there's friction, that wouldn't be quite true, right? And we're also going to ignore air drag. Air drag is very important at higher speeds, but if we just focus on like 0 to 30, it's not going to be as big an effect. So we're making an approximation here, but should be okay. So how quickly would the smart car go? Well, if your power versus time looks like this, then your kinetic energy will get larger with time. So there's the power of the motor, 30 kilowatts, times the time is going to be equal to the kinetic energy. And so if you want to know what the velocity, how quickly the velocity is going to increase, you can solve for v as a function of time, right? So multiply both sides by 2, divide by the mass, right? You end up with something like this for the velocity with time. And you can plot this out if you want. And I can even convert it from, I can use SI units here, kilowatts, convert that to how many thousand watts, kilograms here. I can get this in meters per second and then convert it in miles per hour. And it makes the following prediction for how quickly the car should be able to get up to a certain speed over a certain time. And what's interesting about this is that if you think about the 0 to 30 mile an hour, how many seconds does it take to get from 0 to 30? Then you can draw a dashed line like that. And so it takes about 3 seconds to get from 0 to 30. And I think in a second we'll look that up. We'll look up and find that, in fact, that this is actually pretty close to 3 seconds to go from 0 to 30 miles an hour. So we can also think about this Mustang, which the power that it has, the power of the engine that it has is much larger, but the mass is much larger. The other complication is that the conventional engines cannot just go from 0 power up to full power. So you only get full power when the thing inside of it, the thingies inside of it are rotating rapidly. In other words, high RPMs, right? And so you can't just go from idling RPMs all the way up to like 5,000 or 6,000 RPMs. It takes a couple seconds to do that, and so the power with time is going to look a little bit like that. So initially the power is not much, and then eventually it gets up to the max power. And this power is much higher than the power of the smart car, but we'll see what happens. So I'm defining this T engine as the amount of time, the number of seconds that it takes for this engine to get up to the full power, essentially. And then there's P max as the maximum power. So to get the kinetic energy here, the kinetic energy is the area under this curve. So which is actually kind of what it was before. So even when the power was flat, technically the kinetic energy was the area under the curve, and as more time goes on, the area under that curve gets larger. But if you're going to try to convert this and figure out how this corresponds to the kinetic energy, well, you've got to take the area. And so this is the area. So there's the time here that you're thinking about. You've got the power. The area here, if you remember the area of a triangle, is 1/2 base times height. And so we can use that to figure out what the velocity might be. So 1/2 base times height. So that means that the kinetic energy would be 1/2. The base, I suppose, would be the time, and then the height would be P max times this thing. So if you combine it all together, you get some sort of t squared thing here, like this. And then you want to try to solve for v. Alright, so there's a t squared thing, like I said. You want to try to solve for v, so you multiply both sides by 2, divide by the mass, and you end up with something like this. Square root of t squared is t, so you end up with that. Here's an interesting fact about this. This is constant acceleration, right? So, the velocity is some constant times the time. That's constant acceleration. So we're modeling the Mustang essentially with constant acceleration. So we can plot this out. And we can plot this out of velocity versus time. If we wanted the position versus time, we can go look on our equation sheet. Remember the 1/2 at squared. So for things that are going constant acceleration, that's how the x position advances of time. So this works out to be that, which is kind of nice. Now, the position as a function of time for the smart car is a little bit more complicated. We'll talk about that in a second. But if you just take the velocity as a function of time, which you already knew, basically this thing. So you notice that for the Mustang, this is a straight line. This is a straight line for a while. Eventually, once you get to here, it starts to change that line. But this is a straight line, whereas for the electric smart car, it's more of a curve because it's the square root of the time going on here. And the cool thing is that in these initial seconds, the smart car is moving faster than the Mustang. Like the velocity is faster, and so it's actually going to move further. In that 1 second or so, it's going to move further than the Mustang will. And the video argues that when you're driving in the city, that first second is really what matters for getting around different vehicles. And so arguably the smart car is a better car for driving in the city. When and where do they catch up? Well, this is the velocity graph. Just because they're going the same velocity here doesn't mean that they're actually at the same position. So to do that, you'd have to dig into it a little bit more and take the area under this curve, which I'm not necessarily going to go over. But this is just a nice simple model for these two cars. And the cool part about it is that if you look at the 0 to 30 mile an hour speeds, you'll find that if you look it up on the internet, you'll find the Mustang takes about 2 seconds to get up to 30 miles an hour, and the smart car takes about 3 seconds. So I didn't tune that. I wasn't trying to make sure that happened. That's just sort of what came out of it when I made the assumptions that I did about the mass of the cars and the power of the engines, stuff like that. So there you go. The next part of this is it's pretty silly. There's actually polka music. I don't know if you guys can hear the polka music. So hopefully you've skied before. Ohio's not a great place to go skiing, but never and so there's this little table, and there's a little handle there that people will hold on to, and that will pull them up. So let's imagine that your job is to try to figure out how powerful of a motor do we need to power this ski lift, and to pull all these people up the hill. And so the hill's at a particular angle. We have a certain mass of person. That video goes on for like 20 minutes, by the way. Let me just double check that everything's recording. I think it is. All right. So again, so there's a skier that's going up the ski slope like that. And the question is how much power does, maybe you need to pull 6 of these skiers, each one of them is 60 kilograms. There's some coefficient of friction, right? Because even though it's snow, there's still some amount of friction that's there. And then there's some speed that we're pulling the person up the ramp. I guess I think I should say 20-degree incline, so sorry, that's a mistake. All right, so we can draw the force diagram here. The easiest one is the weight, so the weight is pointing down, as always. There is going to be some force of the cable, the ski lift, pointing up this way. There's going to be the normal force. Yeah, so there's the cable, there's the tension in the cable that's just pulling, right? There's the normal force pushing up at an angle because we're on a slope, right? And then finally there's the friction, which is a force opposite to the tension, because as you're being dragged up this hill, the force is in the opposite direction. So these are the forces that we have to deal with. And there's actually 2 different ways that we can figure out how much power that you need to pull these people up the ramp. And so I'm going to do the way that we've been doing, basically force times distance, and I'm going to think about the energy last. But there's another way to do it, which I'll show you in a few slides, in which you think about the energy first, and it's ever so slightly less complicated, but it's good to be able to do it more than one way. So I'll show you that in just a second. Whoops, oh, that's not good. All right, here we go. So we're going to use our tilted coordinate system, right? Because that's often the most helpful thing to do. By using a tilted coordinate system that allows us to put the tension in the x direction, which is nice. The friction is in the minus x direction. And then the complication is that the weight now is at an angle. So the weight is no longer parallel to the y. So we have to figure out what this trig function is. Here's a question. What do we assume for the acceleration? Put on your thinking caps. This question is usually, is it 0 or non-zero? And the thing to remember is that the question says pulling the skiers up at constant speed. So constant speed, what's the acceleration at constant speed? That would be 0. Okay. And then for the acceleration in the y direction, that's a question of like, so there's a slope here, right? We're accelerating up this way, right? Are we accelerating this way or that way? In the y direction? Or does our height above this, the surface of this hill is changing? No, that height is not changing. So the acceleration in the y direction will be 0, and the acceleration in the x direction would also be 0. I think I should also be a red x here that I should add. So if you realize that this is 0, you can solve for the normal force. And if you stare at the mass for long enough, you can, which is what we're going to do now, we can try to figure out what trig function that this is. So again, this is the component of the weight that's in the y direction. So there is a component in the y direction and a component in the x direction. So if the hypotenuse is mg, adjacent over hypotenuse would be cosine, right? And so the y direction here would be cosine. So we would expect mg cosine theta, right? And then in the x direction, here that's opposite over hypotenuse, so that would be a sine. So this would have to be a sine. Again, this a sub x should be 0, which we just talked about. Okay, getting ahead of myself. All right. So that's what we've got. Here's our trig function. We've got another equation here, but what we can do is we can solve for the tension, right? Because there's a friction force here, but we know what the friction force is because the friction force is the coefficient of kinetic friction times the normal force, right? And we know what the normal force is. The normal force we just found to be mg cosine theta. And so we have conclusively discovered that the tension in the cable is going to be mg sine theta because everyone is heavy and prone to sliding down the hill, but also because there's friction. And if the friction was 0, then you'd only have this, which makes some sense. But the larger this mu sub k is, the more friction you get, the more tension in the line you need to pull these people up the ramp, which makes some sense. So that's what you get for the tension. And if you want to know how much energy that's going to take, force, then that's just force times distance, right? So we had this equation from earlier. Now, just for the record, this angle theta is different from this angle. I did that intentionally because I was wanting to ask you if it is the same or not. And the thing to remember is that this angle is actually the angle between the applied force and the motion. So if you look carefully at the book, that's what it'll say, which means that if you are moving in the direction that the tension force is trying to move you, then the angle between those two things is going to be 0, right? And then cosine of 0, say it with me now, is 1. So again, your velocity is in the same direction as the force. Theta is 0, cosine of 0 is 1. And so the work is just the force times the distance. In other words, the tension times the amount of how many meters that you pull the thing up to the hill. So that's the work. What we're really interested in is the power, right? Because when you go to the store to buy a gigantic electric motor for your ski lift, it's not rated in terms of work, it's rated in terms of power. So how do we figure out how much power that needs? Well, the power is the energy over time, right? So this is the work over some distance, and so we divide that by the time over some interval of time, then it's going to look something like this, okay? Now, delta x over delta t, does that sound familiar to anyone? Anybody? Delta x over delta t, that's the velocity, right? And so the faster the velocity that you want to pull these skiers up the hill, the more power that you need. That makes some sense, right? And the friction matters for how much power that you need. The weight of the skiers matters. Mg, the angle of the hill matters. Steeper hills are harder to pull people up. So this is what we get for the power that you need. So you can run these numbers. You can figure out how much power you need from the electric motor that you need to buy. How much electricity you need to pay for, that sort of thing. The other way to do it is to think about the energy first, and to think about the change in potential energy, those sorts of things. So here's our skier going up the hill, right? And we've talked about the change of potential energy is mg delta h, but is this delta h or is this delta h, right? And the answer is that this is the delta h that you should use, because this is the actual change in height above the ground. And so there you go. And we can write that down. So if this is the delta h, well then the delta x, the distance traveled up the ramp, is like this. Sorry, that's a little bit misaligned there. I could have fixed that. And so delta x relates to delta h by, so it's adjacent over hypotenuse would be sine. So it's going to look something like this. Delta x sine of phi is going to be our change in potential energy. Okay, so that's our change in potential energy. How much energy is lost to friction? Well, the friction force times the distance can tell us how much energy is lost to friction, right? So there's a friction force there. The book uses an equation that looks like this. In our case, it's just delta x, so we can replace that. And then the friction is related to the normal force, which we know how to which we calculated earlier. And so that's going to be, so this much energy is going to be lost to friction as we go from here all the way up to here. Okay. And so we can put all these together. We can say, well, the motor needs to provide the energy to pull the person up the ramp, change the potential energy. That's the whole point. But the motor also needs to provide enough energy so that if there's energy losses to friction, that's fine too. And so the total energy that the motor has to provide for the thing traveling delta x, the person traveling delta x, is this, like that. And then you can ask the same question. All right, well, that's the total amount of energy. That's happening over some time interval. And again, they don't sell motors according to how much energy they can produce. It's energy per second. And so we have to divide this by some time interval. Delta x or delta t gives you a velocity. And so now you can calculate the power. And lo and behold, we find that it's the same equation. Yay! Physics works. All right. So the same answer as before. So it's good to be able to do it in two different ways. I hope this is helpful for homeworks and various other things. But this is what I wanted to cover today. So there you have it.